right, let's get going on today's meeting. So what we're going to be doing today is we are going to be finishing up our look at the chi-square tests, specifically focusing in on the chi-square test for association and how you can do that in SPSS. So this is going to be another hands-on SPSS meeting where we take a look at the test that we laid out the logic for last time and now see how to actually implement it using the tools at our disposal, specifically SPSS. And always remember, this is in service of our goal of using inferential statistics to take psychology out from the lab and into the world, but to do it in a way where our own human biases, our own human hopes and wishes for what we wish was true does not get in the way of what is actually true, because what is actually true is what is actually needed in order to help people in the real world. So again, we are going to do this with some do it with me demos, taking a look at how to run the chi-square test for association in SPSS, how to set it up, how to interpret it, and hopefully avoid some pitfalls along the way. All right, so on the schedule for today, it's going to be an SPSS heavy do it with me demos heavy day. We are going to return to the paper on gender differences in receptivity to sexual offers. So we'll review very quickly Clark and Hatfield's research from 1989, and then Kunsten-Greitmeyer's replication of that research in 2025. And then we are going to, before we dive into the SPSS of chi-square test for association, we're going to talk a little bit about something that is actually beyond the scope of this course. So this is an introduction to statistics course, and I am very intentional about making it an introduction to statistics course. And this is going to be one of the first times where we encounter something that actually goes beyond the scope of this course. So I do just want to mention it so that its omission has an explanation. And then we're going to ask the question and use SPSS to answer these questions. Does the gender of the subject affect whether or not they accept an offer just in general? Does the gender of the subject affect whether or not they accept a date? Does the gender of the subject affect whether they accept an apartment invitation, whether they accept an invitation to bed? And then finally, are these results different in 1978 versus 2025? So we're going to focus in on the 1978 data and on the 2025 replication. All right, so again, focusing on the gender differences in receptivity to sexual offers paper by Clark and Hatfield, and then the follow-up gender differences in receptivity to sexual invitations to naturalistic replication studies by Kunz and Greitmeyer. So just to recap what the two studies were about, Clark and Hatfield in 1972 was when they did their first study. They had female experimenters. So these were female Confederates that went out into the student body, and they also had male Confederates that went out into the student body. And these Confederates would approach opposite sex strangers. So males would approach females, females would approach males. And once they selected a subject, the experimenter would approach them and they would ask them, they would follow a very specific script and then ask them one of three different questions. So once they chose who they were going to approach, they would walk up to them and say, I have been noticing you around campus. I find you to be very attractive. And then they were randomly assigned a question to ask. So they did not choose which question to ask. This was randomly assigned. And they would either ask, would you go out with me tonight? Or would you come over to my apartment tonight? Or would you go to bed with me tonight? And then the dependent variable was, what was the answer the subject gave? Did the subject accept the invitations, or did the subject not accept the invitation? So what was the subject's response for female experimenters asking male subjects? And then what was the response for male experimenters asking female subjects? So once again, exact same script. I've been noticing you around campus. I find you to be very attractive. Either would you go out with me tonight, or they would ask, would you come over to my apartment tonight? Or they would ask, would you go to bed with me tonight? And then once again, the dependent measure was, did the subject respond yes or no? So that was the setup that was used. And the replication was done in 2025. And the original study was done in 1972. So we are going to take a look at both of those studies to see if what happened in 1972 actually differs from what was found in the replication in 2025. Do the answers of the subjects depend upon the time that they were asked in? So in the original study, the main question that they wanted to know was whether or not there was an association. So we talked about associations last time, a relation between two categorical variables. Is there an association between the sex of the subject and the responses to the answers? Another way of phrasing that is asking if knowing the subject is a male or a female, does that allow you to predict their response to the different answers? So is knowing that your subject is male give you the ability to predict what their answers will be? And would those answers be different than if that subject was a female? That's what we're looking for with associations. All right, so just to give you straight from the publication, the information. So study number 1 was conducted in 1978 and study 2 was conducted in 1982. In both studies, 5 college women and 4 college men from an experimental social psychology class served as experimenters. All had volunteered to approach subjects who were either alone at 5 different locations on campus. The Confederates were approximately 22 years of age and were neatly dressed in casual attire. Once a subject was selected, the requester approached him or her and said, I have been noticing you around campus. I find you to be very attractive. The Confederate then asked one of 3 questions. Would you go out with me tonight? Would you come over to my apartment tonight? Or would you go to bed with me tonight? So you can see in the next sentence, thus this procedure resulted in a 2x3 factorial design. Sex of the requester, 1 categorical variable. Type of request, a 2nd categorical variable. And then the chi-squared of test of association would be used to test whether there was an association between those 2 variables. So just to kind of recap again what they found. So in terms of the yes answers, on the x-axis there, we have the type of request was the requester asking for a date, inviting them to the apartment, or inviting them to bed. On the y-axis, we have the frequency of responders. 16 people were approached for each question, and there were 16 females approached and 16 males approached for each question. And the pink bars are going to be the female subjects, and the blue bars are going to be the male subjects. So in terms of saying yes to a date, we have 9 females accepted the date and 8 males accepted the date. In terms of accepting the invitation to the apartment, slightly different story. Only 1 female accepted the invitation to the apartment, but 11 males accepted that. And then accepting the invitation to bed, no females accepted that, and 12 males accepted the invitation to bed. So in this formulation, this is what is known as a 2x3 factorial design. So the way that this convention classifies or labels different experimental designs is basically the numbers indicate how many levels each variable has, and then the number of numbers indicates how many variables there are. So in a 2x3 design, we have variable number 1, and that 2 represents that first variable. And variable number 1 in this case is the sex of the subject, and we label it with a 2 because it has 2 levels. In 1978, it was either male or female. And then we have another variable, and that is indicated by the 3. And the 3 is the type of request, and we label it with a 3 because we have 3 types of requests: asking for a date, asking for an apartment, or asking for a bed. And if this was the design of the experiment, then we could have done the chi-square test for association on this data here. However, this is where we're going to encounter our beyond the scope of this introductory statistical course, because when I looked at the results and discussion in the original paper, I came across this little doozy. And it said a 2 by 3 by 2 multi-dimensional chi-square analysis was used to analyze the date. So it should actually be data. So a 2 by 3 by 2 multi-dimensional chi-squared analysis, without getting into too much detail, that is some advanced statistical analysis. So chi-squared for association, appropriate for an introductory to statistics course. Multi-dimensional chi-squared analysis, you'll come across that in grad school. So unfortunately, we're not going to be able to do the full design, but I do want you to understand where this 2 by 3 by 2 actually came from. And it comes from the fact that in order to do the chi-squared analysis of this, we cannot simply include the yes answers. In order to do the analysis properly, and again, we won't get into why this is required because again, that is graduate school level statistical reasoning, but just for your own information, if we were going to analyze this correctly, we would have to analyze the yes responses and we would have to analyze the no responses as well. So there's the pattern for the yes responses. There's the pattern for the no responses. There's the two of them together, and this is the situation that we would need to analyze in order to do a proper chi-squared analysis of this data. And this takes it beyond our course's scope because this is that 2 by 3 by 2 design. 2, because we have 2 levels of one categorical variable, sex of the subject, female versus male. 3, or times 3, because we have 3 categories of questions, date, apartment, or bed. And then finally, another variable, 2, which is the response. Did they respond yes, or did they respond no? So that 2 by 3 by 2, that extra 2 at the end, where we have to include the no responses pattern and the yes responses pattern in order to correctly do this, that takes it out of the scope of this course. So we are not going to be able to do the actual 2 by 3 by 2 multi-dimensional chi-squared analysis used to analyze the data. However, that does not mean that we're not going to be able to replicate any of the analyses here because they did, in order to dive down deeper into the results, they did do a chi-squared test for association, and that is in this line right here. So in study number 1 conducted in 1978, the results indicated that men were more likely to say yes to each type of invitation than were women, 65 versus 21%, chi-squared with a degree of freedom of 1 equals 18.78, p-value less than 0.001. So why does this all of a sudden become something that we can do a chi-square test for association? Why does this take it from a 3-variable design down to a 2-variable design? Well, the reason is because they are now asking, are men more likely than women to say yes to any kind of invitation? So they've taken that invitation variable and they've collapsed it down to just one category, the invitation. And that removes it, allowing us to do a chi-square test for association with just 2 variables. So basically what they did is they took all the women that were asked, would you go out with me tonight? And they took all the women who were asked, would you come over to my apartment tonight? And they took all the women who were asked, would you go to bed with me tonight? And they put all of them into the same category. Basically, what was your answer to would you tonight? So they took all 48 subjects who were asked a question, all 48 female subjects who were asked a question, and just collapsed them into one category. You were asked a question, did you say yes or did you say no? And then they did the same thing with males who were asked these questions. They collapsed them. So we're not looking at individual questions or the different question types now. We're just looking at when invited to some sort of an intimate rendezvous, was there a difference between subject sex and their likelihood of saying yes? All right, so that is something that we can do. So let's set it up here. Much like every other test that we have our null hypothesis, we have our alternative hypothesis. So in this case, the null hypothesis, because of the complexity of these associations, we write it out in English, and the null hypothesis is simply there is no association between subject sex and the likelihood of saying yes to a general invitation. And then the alternative hypothesis is just the complete opposite of that. There is an association between subject sex and the likelihood of saying yes. So what does that look like visually? We're talking about associations. So let's put that in a more visual context here. So here are the results when we collapse across the type of question. So on the y-axis there, on the x-axis there, we have the answer that the subjects gave. So did they say yes or did they say no? The pink bars are the female subjects, the blue bars are the male subjects. Y-axis shows the frequency that these responses occurred. So you can see that females answered yes, 10 females answered yes. Looks like approximately 31 males answered yes. 38 females answered no, and it looks like 16 males answered no. So the null hypothesis, let's start with the alternative hypothesis. The alternative hypothesis is that there is an association between subject sex and the likelihood of saying yes. And basically what that boils down to is that the pattern that we have here, the effect that we have here in the yes condition, does not equal the pattern that we have here in the no condition. That is what the alternative hypothesis is telling you. That there is an association basically means that the pattern of yeses does not match the pattern that we get for the no responses. And then the null hypothesis is that there is no association between subject sex and the likelihood of saying yes. And that means that the pattern for the yes responses actually does equal the pattern for the no responses. So even though the bars look different to our eyes, the null hypothesis is that that variation, that difference, that's just random chance. That's just the way that the dice rolled on that particular day. And if we replicated it, it wouldn't have this pattern again. So what the null hypothesis is saying is that these differences that seem visually apparent, they're actually just random chance. And if we ran this experiment again, we would get a different random variation, and that the actual patterns are not real patterns. They don't really exist. There is no association. So now that we kind of have a visual of what we're looking at, let's actually run the data. And for that, we're going to go back to SPSS, and we're going to get our data from the chi-squared association SPSS demo Excel sheet. So if you haven't already, open that up. There is a link in the description if you're watching this on video. And what we have here is we have first combined across all questions the responses of the subjects. So we have our female subjects, one in each row, that said yes to any invitation. We then have our female subjects, one in each row, that said no to any invitation. We have our male subjects, one in each row, that said yes to any invitation. And we have our male subjects, one in each row, that said no to any invitation. And now we're going to see if there is a different pattern for males in terms of saying yes and no compared to females in terms of saying yes and no. So for that, we are going to first transfer our data here, our raw data, into SPSS. So we're going to highlight all the data. So Shift, use your arrow keys, Control Shift to highlight all of your data, Control C to copy it. We are going to allow this if your browser does that. Then we're going to go over here to SPSS, and in row 1, column 1, we are going to paste that, and we're going to allow. And it's going to do that thing where it gives me the V. So we're going to delete that V, and we're going to paste it, and we now have our data put into SPSS. In this case, and don't ask me why, first thing that I'm going to mention in this is that when we were doing chi-squared for goodness of fit, remember we had our data formatted like that. And then we had to assign numerical values to each category. So we had to assign, for example, a 1 for female subjects, a 2 for male subjects, a 1 for the yes response, a 2 for the no response. We needed to do that when we were doing goodness of fit. For some reason, when we're doing a chi-square test of association, that is not a requirement. So actually having the data in this string form, in this word form, is completely acceptable. And once again, we make sure that every single row is a single subject, and every response from each subject goes onto their and only their row. So we have that done. Next thing we want to do is we want to change these variable names. So we go over here to variable view, and we are going to change variable 2 to sex, and then we are going to change variable 3 to answer. So now we have sex for whether the subject was female or male, answer for whether they said yes or no. So now we are going to do the chi-square test for association. And if you remember when we were doing the chi-square test for goodness of fit, we would go down to, we would go to analyze, we would scroll down to non-parametrics test, we would go to legacy dialogues, and we would go over here to chi-squared. That is not at all where we're going now. So first thing to note is that the chi-squared for goodness of fit is nowhere near where the chi-squared test for association is in SPSS. Where we need to go instead is we're going to go to analyze. We are going to go to descriptive statistics. And then we are going to go down here to crosstabs. And that is the test for the chi-squared test for association. So SPSS is not being friendly at all. SPSS is calling it crosstabs instead of chi-square test for association. But just one more time, we go to analyze, we go to descriptive statistics. Now for the first time, we go to crosstabs, we click on that, and it brings up the crosstabs dialog window. So what we need to do now is we have our 2 variables, and we need to tell SPSS which variable do we want in the rows and which variable do we want in the columns. It is not going to make any difference in the final analysis, in the statistical output, which one you put in rows and which one you put in columns. Typically, the convention is you put your explanatory variable in rows and you put your explained variable, your dependent variable, in columns. That's typically the way that it is done. So because we're wondering, does sex influence the answers, we're going to put sex in rows, and then we're going to click on answer, and we're going to use the arrows to move answer into columns. And if you make a mistake, you can just click on them and move them back out. Not a problem at all. And then very importantly, we are going to go to statistics here, the statistics options. And this is where you can now tell SPSS to do the chi-squared analysis. So we're going to click on chi-squared here. And then we are also going to click on phi and Kramer's V. And this is a measure of effect size. And that's it. That's all that we're going to click on for this particular test. Now, this is one of the first times that we had multiple options when we were doing our test. And one thing that you want to do when you're using SPSS or any other statistical package is you want to keep your options as lean as you possibly can. And it might be something that you might think would be very interesting, and maybe you would gain some real insight if you clicked on all of this and generated all these tables and really dug down deep into the stats. That is an error, because all you're going to do is end up confusing yourself and end up with an output that's 20 pages long and makes it really difficult to find the correct information. So we're going to keep this as lean as we possibly can. We're going to choose chi-squared. We're going to choose phi and Kramer's V, and then we're going to hit continue. And then over here in the cells, you can choose different cell displays. So much like In other chi-squared tests, you can choose your observed counts. You can choose the expected counts if you need chi-squared to calculate expected counts for you. So for example, if you're doing your homework and they require you to report the expected counts, you can click on that and SPSS will calculate those for you. You can calculate the percentages for the rows, for the columns, and for the total. You can do that as well. However, we are just going to keep the counts as the observed counts. We're going to keep it lean so that it's not confusing. So that again is over here in cells. So once again, in statistics, chi-squared, phi, and Kramer's V, and that's it. In cells, just the observed counts, and that's it. And then once we have all that, we can hit OK. And we get our output. So has everybody achieved that output? All right. Well, let's take a look at what that actually says. All right, so this is the output, and we are going to actually ignore that top table there. It basically just lets you know if you have missing cases or how many valid cases you have. So we don't need to concentrate in on that. We're going to concentrate in on these three tables here. So the first table is this top table here that is labeled with your two variables and then cross tabulation. So this is sex multiplied by answer cross tabulation. And this is where you want to just double check that you have the right number of responses in every single category. So on this table here, we can see that for the sex variable, for female subjects, we have 38 that answered no. We have 10 that answered yes. We have a total of 48 subjects across those two conditions. That checks out. That's what we wanted to enter. So we know that we've entered in our data correctly for the female subjects. For the male subjects, SPSS lets us know that we have 17 males that answered no, 31 males that answered yes, for a total of 48 males. Again, that is exactly what we wanted to enter. So it gives us confidence going forward. And then it also organizes these by answer. So in this case, we have the yes column over here. 10 females said yes, 31 males said yes, for a total of 41 yeses. And we have the no column over here. 38 females said no, 17 males said no, for a total of 55 no's. So always, always, always double check that top table. And if the top table does not match what it needs to match, you got to go back and re-edit your data. There was a mistake made somewhere, and the rest of the output is just going to be false. All right, now on to table number 2. So this chi-squared tests table, this is where you're going to find your chi-squared statistic. So the chi-squared statistic is this Pearson chi-squared value right here on this first row. So the value that we calculated is 18.774. That is your chi-squared statistic. Your degrees of freedom, in this case, SPSS has calculated it for you. Your degrees of freedom is 1. And then the p-value is this p-value right here, the asymptotic significance. So once again, it's not referred to as p-value or anything with probability. This is less than 0.001. So just again, to tie this in to the chi-squared distribution, if you take a look at the chi-squared distribution with degrees of freedom of 1, and we plot that distribution, and then we plot the value, the chi-squared value that we calculated for our pattern of data, and we calculate that area, basically on this chi-squared values here, 18.74 is all the way over here, which would indicate that we would have a very, very, very minuscule probability of getting a sample this weird if there was no association between sex and accepting an invitation. So if it is a minuscule probability that we would get a result this weird if there was no association, that means that our weird result is more probably because there's an association. So we have a p-value of less than 0.001. So in this case, we would reject the null hypothesis that there is no association, we would accept the research hypothesis or the alternative hypothesis that there is an association, and that is exactly what Clark and Hatfield concluded. So again, in study one conducted in 1978, the results indicated that men were more likely to say yes, i.e. there is an association to each type of invitation than were women. So again, this is the idea that an association lets you predict. And if I told you I'm thinking of a subject, did they say yes or no? You would have a very poor time of trying to predict whether they said yes or no. But if I said it was a male, well, now you can predict with 65% accuracy that they were going to say yes. And if I said no, it's actually a woman, you can predict with a 21% chance that they said yes and a 79% chance that they said no. So knowing the sex of the subject allows you to predict whether they said yes or no much better, hence the association. And if you recall the numbers that we found in our chi-square test, 18.774 degrees of freedom 1 and a p-value of less than 0.001. That is here in this study. So there's the chi-squared statistic reported in the study, 18.78. There's the degrees of freedom. And then there is the p-value, just like we calculated in SPSS. All right, so any questions on that first analysis for the chi-square test of association? All right, so that's what happened in 1978. Now we're going to take a look at what happened in 2025. So gender differences in receptivity to sexual invitations to naturalistic replication studies. Basically the exact same procedure done in 2025. And what they found, just to jog your memory, was this pattern of data. So the first thing that kind of jumps out, and this is for the yes responses, the first thing that kind of jumps out is that the number of yes responses, even though they went to the same number of subjects, 16 in each category, the number of yes responses is way lower than in 1978. So again, we're going to ask whether that is a real difference or is this just a chance occurrence? So 8 men accepted a date in 1978, only 4 men accepted a date in 2025. Is 8 versus 4 really that different? Or did they just happen to come across 8 males who were rather promiscuous in 1978? And if they tried it again, maybe they would only get 4. So again, that's the kind of question that we're asking. So this was the pattern of data for the yes responses. This is the pattern of data for the no responses. Again, to analyze the entire data set would require a 2 by 3 by 2 multi-dimensional chi-squared analysis. So we are also going to do what Coons and Greitmeyer did, and we're going to once again collapse across question. So rather than asking, did the type of question affect their responses, we're just going to focus in on whether the sex of the subject affected their responses by taking a look across all questions. So how did female subjects respond to would you accept this invitation tonight? And was that pattern different than male responses to would you accept this invitation tonight? So once again, it's the same exact null hypothesis. Null hypothesis, there is no association between subject sex and the likelihood of saying yes. Alternative hypothesis, there is an association between subject sex and the likelihood of saying yes. And again, these are phrased in English terms because to put them in a more mathematical formulation with equal signs would be extremely complicated and would get more complicated the more conditions you had. So the idea is that we'll just mention them in English, and it's just null hypothesis, no association. Research hypothesis, there is an association. So once again, what does that mean? Well, if we take a look at the data collapsed across questions, on the x-axis there, we have the answer that the subjects gave. Did they say yes or did they say no? Y-axis, we have the frequency that those answers were given. Pink bars are the female subjects. Blue bars are the male subjects. The alternative hypothesis is that there is an association between subject sex and the likelihood of saying yes. And what that is saying is that the pattern of responses that we have for the yes answers does not equal the pattern of responses that we have for the no answers. That's what an association means, that the two patterns are not the same. The null hypothesis, on the other hand, is that there is no association between subject sex and the likelihood of saying yes. So what that means is that the pattern of yes responses equals the pattern of no responses. And if the null hypothesis is true, that just means that even though those bars look like they are different patterns for yes and for no responses, it's really just chance occurrence. It's really just random variation. And if we ran this experiment again, we wouldn't find this pattern. So there's actually no real association between subject sex and the likelihood of saying yes. So is that the case? Has that changed since 1978? Well, let's take a look. So for this one here, again, we have our output. We'll go back to SPSS. We have our output. We've already analyzed that. So if we needed to save this, we could save it over here. But for purposes, we're just going to close out of it. And then we have our two variables here. And what we're going to do is we are going to highlight those two variables by clicking on the top of each variable where we can highlight the entire variable. And we are just going to delete out so that we don't get confused. And we are going to repaste in new information, this time going away from the Clark and Hatfield 1972 data. And down here on the Excel sheets, we are going to go to KNG all Qs, which is the Kunz and Greitmeyer 2025 combined across all questions data. So once again, this is set up exactly like the previous data because we're going to run the exact same type of test. So the formatting has to be the same. So once again, we have the females that answered yes. We have the females that answered no. Everyone gets their own row. We have the males that answered yes, and one male that answered no. We have the males that answered yes and the males that answered no. So we are going to transfer all of that data. So we highlight the first two cells, Control Shift, arrow down to highlight all of the responses. Control C to copy. We go over to IBM SPSS statistics. Column 1, row 1, Control V. Column 1, row 1, Control V. Let's try that again. Sometimes you just got to go to the file commands instead, I guess. That does not bode well, but we'll see. We'll see what we're going to run into. So once again, now we have the horrible var 00004, var 00005 names. So we're going to go down here to variable view. We're going to change that to sex and answer. We go back to data view, and now we have nice labels that make sense. And then once again, we're going to do the exact same test. So we are going to go up here to analyze. We're going to go to descriptive statistics. We're going to go down to crosstabs. And then we're going to once again put sex in the rows and answer in the columns. And then when we now choose our statistics and our cells, you're going to notice that SPSS remembers your previous selections in the same session that you're working on SPSS. So this is something to just be aware of, because if you want to change something, say we no longer wanted phi and Kramer's V, then we would have to unclick that because SPSS remembers your options. Now this is wonderful if, like what we're doing today, you have to run multiple tests over and over and over and over again. It's absolutely horrible though if you forget about it and you need to change something about your tests. So just be aware, SPSS does remember what you did in that session. Once you close out of SPSS, you're going to have to re-enter in all those options. So use that information to your benefit. So once again, we hit continue. On the cells, you can see that observed are chosen. If you need expected, you can choose them right there. We do not, so we're going to hit continue. And then we hit OK. And we have our output here. And once again, it looks very, very much like the output that we had previously. So hopefully yours looks like that, and we can dive right in and check out what they found in 2025. All right. So that's the output right there. Let's zoom in. So once again, we don't really have to take a look at that top table because we're not missing any cases. All our cases are valid. So we are going to focus in on this table right here, sex multiplied by answer cross tabulation table. And again, this is where you check to make sure that you put the data into SPSS correctly. And I will always mention this because if you get that wrong, the rest of it doesn't matter. You have to enter in your data correctly, and it's worth the extra 2 minutes that it takes to just double check to make sure that it is correct. So once again, for the variable sex, we have the data for females. That checks out 46 no's, 2 yeses, total of 48. We have the data for the male subjects, 35 no's, 13 yeses, 48 total. We have the data for the answers. For females, 2 yeses. For males, 13 yeses for a total of 15. And for no's, we have 46 females, 35 males for a total of 81. So you can see, very interestingly, very many no's, very few yeses, but the data was entered in correctly. So now we can move forward with confidence. All right, so for the chi-squared test value here, this is where you find your chi-squared statistic. And we have our Pearson chi-squared statistic calculated 9.560 with 1 degree of freedom. And we have our p-value of 0.002. So this is, once again, our chi-squared statistic. Our p-value is the chance of getting a pattern of data this extreme if there was actually no association between the two variables. So once again, we can go back to our chi-squared distributions. And now instead of this chi-squared statistic, we have this new chi-squared statistic of 9.56. So if we enter that in, 9.56, this time we actually get our value on the axis here. So we have our chi-squared value right there of 9.56. And if we could see it, there'd be a blue area here that was 0.2% of this distribution. And again, this distribution, this is your null hypothesis distribution. These are all the patterns that we would get from samples of this size. Actually, from samples of this experiment, these are all the patterns that we would get if we ran this over and over and over and over again. And if we did this over and over and over and over again, only 0.2% of the time, only 2 times in 1,000, would we just randomly get data that was this weird. Well, if it only happens 2 times in 1,000, if there's no association, that gives us pretty strong evidence that there actually is an association. So in this case, we would accept the alternative hypothesis that there is an association and reject the null hypothesis, because the null hypothesis would only be true 2 out of 1,000 times. All right. And now we are also going to go down to this table here of symmetric measures. And this one we are going to take a look at this time, because this is where SPSS will calculate effect sizes for you. And an effect size, we don't really talk too much about effect sizes, but we're going to focus in a little bit on it today because there is an interesting result that's going to come up later. But in terms of effect size, we have Kramer's V, which is what Kuntz and Greitmeyer are going to report. And it has a value of 0.316. And Kramer's V can vary anywhere between 0 and 1. And 0 is no effect whatsoever. 1 is a very large effect size. So it gives you a way of sort of measuring not just is your effect there, but also how big of an effect is it actually. All right, so we have that information. Chi-squared statistic of 9.56, 1 degree of freedom, p-value of 0.002, Kramer's V of 0.316. And you can see here in the write-up for this report, in line with hypothesis number 1, a chi-squared test for independence revealed that significantly more men than women, 27% versus 4%, accepted an offer chi-squared chi-squared of 9.56 with 1 degree of freedom. There's your p-value, and then there is the Kramer's V effect size calculated and reported, and this is where they actually got that data from a chi-square test of association. All right, so any questions on this analysis so far? All right, well, now we're gonna go a little bit off script. Excuse me. We're gonna go a little bit off script, and we are going to do some analyses that weren't reported in either study for 2 reasons. One, to illustrate the chi-square test for association and some of the things that you can do with it. And 2, also because it's just very interesting to do these types of analyses when you have questions that you want to ask that aren't necessarily analyzed in the studies that you are looking at. So for example, is there a difference between males and females for the specific questions? So remember that we couldn't analyze the difference between males and females and all of the questions together, but we can drill down into each individual question and use the chi-square test for association to see if there's an association there. So for example, we can go back to the 1978 data and we can say, is there an association between the sex of the subject and their answers to, would you go out with me tonight? So is the pattern of responses for women to the question, would you go out with me tonight, is that actually different than the pattern of responses for males to the question, would you go out with me tonight? So we only have one question, so it's not a variable, right? It's only the one question that we're looking into. So now we have a 2x2 male versus female, yes versus no analysis, and we can do our chi-square test of association. So the null hypothesis, there is no association between subject sex and the likelihood of saying yes. Alternative hypothesis, there is an association between subject sex and the likelihood of saying yes. So the data for this particular question looks like this. So once again, x-axis is the answer to the question. Did they answer yes? Did they answer no? Y-axis is the frequency, how many subjects said each response. And then the pink bars are female responses, blue bars are male responses. And the alternative hypothesis is that there is an association between subject sex and the likelihood of saying yes. And again, just to kind of drive this idea home, what that is saying is that the pattern of data here for the yes columns does not equal the pattern of data here for the no columns. And this is the first time where visually it kind of looks like they might be pretty close, right? We have pretty close responding for the yeses for male versus female. We got pretty close responding for the no's for male versus female. It might not actually be the alternative hypothesis supported this time. There might not actually be an association. It might actually be that the null hypothesis is true, that there is no association, so that the pattern of yeses actually equals the patterns of no in this case. So is that actually the case, or is this difference big enough that the alternative hypothesis is going to be supported? We are going to find out when we run that chi-squared analysis. So we'll go back to SPSS first. We'll clear out, close down our output, and we'll clear out our variables. And we are going to see if this works. And if not, I'm going to give you the workaround to get around it. So we are now going to go not to CNH all Qs, but we're going to go to CNH date. We're going to go to this sheet in the Excel sheet down here. So CNH date. So you should have the question there, would you go out with me tonight? That is what we're looking at. We have the females that said, yes, I will go out with you. The females that said, no, I will not go out with you. The males that said, yes, I will go out with you. The males that said, no, I will not go out with you. 16 females, 16 males were asked for a total of 32 subjects. So we are going to select all of those, copy, Control C, go back to IBM SPSS statistics, Try Control V again, not working again. So we're going to go to edit and we are going to paste. We are going to do the same thing we did before, variable view. We can now call variable, that top variable sex, variable 7, we will label as answer. And once again, notice that we're labeling these the same things every single time, simply because that's what makes the most sense. And just to also illustrate that this really is the same type of test, just done over and over and over again. And the more you understand statistics, the more you see that it's basically just the same 7, 8, 9, 10 tests that are being used in the correct situation, but just over and over and over again. So now we go to analyze, descriptive statistics, crosstabs. Sex we're going to put in rows because that is our explanatory variable. Answer we're going to put in columns because that is the dependent variable. What did they answer? Statistics still has chi-squared and find Kramer's B selected. That is fine. Cells still has only observed selected. That is fine. We are going to hit OK. And this is exactly why I wanted to do this and why I wanted to show you this. Something went wrong here. So as you can see, if we take a look, see if I double click on that, it gets absolutely no bigger. If we take a look at this sex times answer cross tabulation table here, you can see that this mysterious column here has appeared. We have answer and we have blank answers, we have no and we have yes. And apparently there are some blank answers here. And in terms of the sex of the subject, we have blank and we have female and we have male. So I do not know why this happened. I have a suspicion it's because our previous data had 96 subjects and our current data only has 32, but we deleted that data, which worked fine for t-tests, but it does not work for the chi-squared test for association. So I wanted to run this just to make sure that this is actually what is happening so that you don't make this same mistake. And this is also one of the reasons why you definitely always want to check your tables. Because if we didn't check our table, we might go right down here and just report this incorrect statistical data. So you need to check your tables. Clearly something really wrong occurred. So we are going to close out of the output and we are going to realize that highlighting these and just deleting them does not work for the crosstab for association. I have no idea why. It was rather annoying when I discovered it myself. So what are we going to do instead? Well, what we're going to do is we're going to go up here to File, and we're going to go here to New, and we're just going to open up an entire new data editor. So we're going to open up an entirely new data file. So again, go to File, go to New, hit Data, and then you can see that we now have untitled dataset 2, and that is the dataset that we want. We have apparently lost dataset number 1, but that is okay. So again, File, New, Data. Now it's actually working the way that I expected it to. All right, so you can see here Untitled 3, Dataset 2. We're going to use that. So if you click on Untitled 2, Dataset 1, you can go up here to this X and just close out, and it'll close it out so we don't get confused. But now we have a fresh data set, fresh data editor, and we're not going to run into that problem again. So we go down here to chi-squared for association. We still have our data highlighted. We copy it. We go here, edit, paste. We have our horribly named variables. And you can tell that we're in a new data editor because the variable numbering has gone back to 0 to 1s and 2. So we go here and we have sex. We change our names in the variable view. Answer. Go back to the data view. It's all nicely set up. Now we go to analyze. Now we go to descriptive statistics. Now we go to crosstabs, put sex in the rows, put answer in the columns. And now, if I'm not mistaken, yes, because we opened the new data editor, the options that we previously selected are gone. So we have to reselect what we want to do. So we want chi-square, we want phi and Kramer's V. We're going to hit continue. So again, that's in the statistics options. In the sales options, observed is by default selected. We could select these other things if we were interested in them, but we're going to keep it simple and just go with the observed. And then we're ready to go. We hit OK. And now when we look at our sex times answer cross tabulation, that makes sense. That's what we wanted to see. So we now know that we have done the analysis correctly and we can proceed with confidence, knowing that we have put in the right data, and more importantly, SPSS has used the right data. All right, so what does it all mean? Oh, let's zoom in on this. So once again, you saw it in action where it basically saved us from making a horrible, horrible mistake. But we have our table here for sex times answer cross tabulation that lets us know that we now have the correct number of female subjects in each condition. We have the correct number of male subjects in each condition. We have the correct number of yes responses. We have the correct number of no responses. We've entered in the data correctly. SPSS has analyzed the data correctly. So now we go down to our chi-squared tests, and our chi-squared statistic, our Pearson chi-squared statistic now has a value of 0.125. Degrees of freedom of 1, and a p-value of 0.723. So what that means, to put that again into a visual context, we have our degrees of freedom of 1. We now have a chi-squared statistic of 0.125. And if we calculate the area in that chi-squared statistic, you can see that almost the entire graph here is now colored in blue. A little hard to see, but you can see that the entire graph here is colored in blue. What this is saying is that that area is 72.37%. This means that we would get a pattern, we would get a sample that would have this chi-squared statistic or higher. We would get a sample with this pattern or a more extreme pattern 72% of the time. There's a 72% chance that in the null hypothesis world, where there is no association between sex and the answer of will you go out on a date with me tonight, there's a 72% chance of getting a sample as extreme as the one that we found. So that lets us know that there is that 72% chance that our sample came from the null hypothesis population. So in this case, our p-value is very high. We would accept the null hypothesis. We would reject the research hypothesis or the alternative hypothesis, and we would say there is no evidence for an association between the sex of the subject and whether or not they accept a date. And then we have our measures of effect size down there, and we have our Kramer's V, and you can see that we have a non-significant value and we have an extremely small Kramer's V, indicating that there is absolutely no effect for the sex of the subject on whether or not they accept a date or not. So in 1978, the sex of the subject had no association with whether or not they accepted a date. What about 2025? Is there an association in 2025 between how females answered, would you go out with me tonight, versus how males answered, would you go out with me tonight? Null hypothesis, there is no association between subject sex and the likelihood of saying yes. Research hypothesis, there is an association between subject sex and the likelihood of saying yes. These are the results. X-axis, the answer, yes or no. Y-axis, the frequency with which subjects gave those answers. Pink bars, female subjects. Blue bars, male subjects. Alternative hypothesis says that there is an association between subject sex and the likelihood of saying yes, meaning that the pattern here that we see, where males say yes more often than females, is different, does not equal the pattern here where females seem to say no more often than males. So it seems like it's a reversal. So if it is an association, those two patterns are different. However, the null hypothesis says that there's actually no association between subject sex and the likelihood of saying yes. It says that those two patterns are equal, and that really the difference that we see visually, that's just random occurrence. So in the yes category, 4 versus 2, what are the chances of running into 4 people that'll say yes versus 2 people that'll say yes? That seems pretty close. In the no category, 14 versus 12, again, that's pretty close as well. Maybe there really is no association and the patterns just visually look like they might be different. Well, that's what we use statistics to answer. So we're going to go back to SPSS and we're going to clear out of this so we can close our output. And then just to be on the safe side, we're going to go up here to File and we're going to put in we're going to open up a new data editor. So we have our new data editor down here. So we can go back to our old data editor, untitled, and we can close that. We don't need to save it. And now we have a fresh data editor so that we won't get our chi-squareds all jumbled up and confused. We're going to go to KNG date. So this sheet down here is the Kuntz and Greitmeyer "Would you go out with me tonight?" data. And we're going to highlight the scores. So again, all the females that said yes, all the females that said no to a date, all the males that said yes, and all the males that said no to a date. We're going to highlight those scores. We're going to copy that, go into IBM SPSS statistics. We're going to use the edit file options to paste. We're going to rename these two variables. So again, we know that we have a fresh data editor because our variables are var 00001 and var 00002. So we are going to rename those sex and answer. And then we go down to analyze, descriptive statistics, cross tabs, sex goes in the rows, answer goes in the columns. Again, in terms of the actual chi-squared statistic that is calculated, that does not matter. You could put answer in the rows, sex in the columns. This is just the convention that is used. For statistics, we want chi-square and we want phi and Kramer's V. And then for cells, we're going to just keep it as observed. And then we hit OK. And we have our results here, which are the wrong results. What happened? Yeah. What did you do to me, SPSS? All right, so once again, a wonderful example of why you always check that cross-tabulation results there. So let me just close this and see if I can get to the bottom of this. This did not copy and paste correctly. Copy. There we go. All right, analyze, descriptive statistics, cross tabs. Okay, there we got the right numbers. All right, so twice in one day, we have a very, very good example. Why I always harp on checking that top table so that you can be sure that you've entered the data incorrectly. Because I thought I did. I was 100% sure. And yet SPSS pulled a fast one on me. I don't appreciate it, SPSS, but it's hard to stay mad at you. But just always double check. It'll save you a world of hurt. Okay, so we'll do this analysis, and then it looks like we're running out of time, so we're going to save the final analyses for next time. But let's wrap this one up, and then we will just kind of do a little bit of a closing thought experiment for all of you. But once again, saved us twice just in this little run through here. Always check the descriptive data. Make sure that you have the right number of females with the right number of no's and the right number of yeses, the right number of males with the right number of no's and the right number of yeses, the right number of yeses with the right number of female and the right number of males, and the right number of no's with the right number of females and the right number of males, make sure that you check those, because as you just saw, sometimes SPSS tries to pull a fast one. All right, and now we have our chi-square test over here, and we have our Pearson chi-squared value of 8.21 with 1 degree of freedom, and that gives us a p-value of 0.365. So if we just one more time to visualize this, if we go here and we enter in our new chi-squared statistic of 0.821, and we calculate that area, that is the number of samples that would give us a chi-squared value as extreme or more extreme than what we found if the null hypothesis is true and there's no association. We would find a chi-squared this extreme in about 36.5% of the samples that we did if we did this over and over and over again. So we have a 36.5% chance that our sample came from the null hypothesis population. That is not enough to reject the null hypothesis. So we fail to reject, we accept the null hypothesis, and we say that there is no association between the sex of the subject and whether or not they accept a date. And then just to complete our analysis, we have our effect size measures of Kramer V, and you can see also a very small effect size for this result as well. So that is where we're going to wrap up today. What I will just give you, I'll give you a challenge for next class. So for next class, we are going to wrap up our look at the chi-square test for associations. But we do have the data. We just saw the analysis for the data for the question, would you go out with me tonight? But we do have the data for would you go to bed with me tonight already prepared. So I would recommend give it a shot, analyze this data with the null hypotheses and the alternative hypotheses. And importantly, the output is there for you to double check your answers against. So we have the data ready to go, and it is in the Excel sheet. So we have the data for the 1978 study. Would you come over to my apartment tonight? At the C&H apartment Excel sheet. And in the K&G apartment Excel sheet, we have the data for the 2025 replication. And then in SPSS, we have the results for those for both the 1978 study and then also for the 2025 study. So I would highly recommend just to make sure that you have that down and ready to go, good, solidified in your mind. Definitely give those a look. And then we are also going to be able to not actually do, but interpret the overarching question of whether there is an association between subject sex and question type and the likelihood of saying yes, and whether or not that changed in 2025 versus 1978. And then we're also going to wrap this up by taking a look at some of the reasons why, well, I guess this will be a spoiler, some of the reasons why that actually did change across the two time periods. So we'll take a look again at how to interpret that result that is out of our scope for calculating it, but very importantly, not out of our scope for understanding it. And we are going to wrap up our look at gender differences in receptivity for the 1978 and 2025 study, but we were going to save that for next time. So do give those chi-squared test for association a go. Double check your answers against what is going to be available there in the video. So just one more time so it's a little easier to find. There is the 1978 data for would you go to bed with me? And then here is the 2025 data. 2025 data for would you go to bed with me? So we are going to take that up next time. So give it a shot, see if you can get that to match up. But other than that, unless there are any questions, we are done for today.